Hey guys, today me and my group consisting of Johan, me, Melissa and Jiawei will be presenting our engineering exploration project. Our title is Smart Retail Clothing Technology. Let's go through the table of contents for today. For part 1, we will be going through our research and background, consisting of problem analysis and our driving question. For part 2, we will be going through our project introduction, consisting of our solution, design implementation, diagrams, and code. So, our driving question. How can we design devices to improve clothing sales and understand customer demand in retail stores at the same time? For our background, we have decided to focus on fast fashion. Fast fashion has become an increasingly popular strategy among clothing brands to maximize on current fashion trends. It involves the rapid designing, production, and distribution of clothing. This strategy is unsustainable as the fast-changing trends lead to clothing being disposed as textile waste instead of being sold due to becoming outdated. Further research has led us to the discovery that 92 million tons of textile waste is produced every year. For example, H&M had $4.3 billion in unsold clothing. Burberry destroyed 28.6 million pounds worth of unsold clothes, accessories, and perfumes. Fashion firms including Burberry destroy unwanted items to prevent them from being stolen or sold cheaply. Our project aims to develop more sustainable and profit-driven practices in the fashion retail industry to reduce textile waste and encourage environmental sustainability. Now, I will pass it on to Johan, who will be doing our project introduction.
Thank you, Melissa. Now, I'll be further discussing our project and how our solution helps solve our driving question. Firstly, we made a prototype to simulate the inside of a typical clothing retail store. In our prototype, we also have a counter, we have a shelf, and finally we have a shirt fitted with a RFID tag. For the sensors we used, we have a light and RFID sensor and an angle unit placed on the counter. We have an ENV2 sensor and an RGB unit that is placed on the ceiling. We have a PIR sensor that is placed outside with a hole that allows the PIR to detect only the clothing item that is on the shelf. And finally, we have a TOF sensor that is placed at the bottom of the shelf, facing the legs of the customer such that it can detect the distance between itself and the customer. Now for the features. First, we have the temperature monitor, which uses the ENV sensor to measure the current temperature in the clothing retail store. The staff can also change the range of values that is considered optimal by using the 3 buttons on the M5stack. Secondly, we have the sales monitor, which uses the RFID sensor to monitor the number of sales at the counter by scanning the RFID tag of each clothing item as they are being purchased. Third, we have the light regulation, which first uses the light sensor to detect the light intensity in the room. If it is considered too bright or too dim, we can then use the angle unit to adjust the brightness of the RGB unit such that the optimal light intensity can be achieved. Then, we have the first popularity tracker, which uses the TOF sensor to detect if someone is nearby the shelf of the particular clothing item. We can then monitor the time spent by the customers at the area near the shelf of the particular clothing item. Finally, we have the second popularity tracker, which uses the PIR sensor to monitor the number of times a particular item of clothing is taken off the shelf. We have also done further research on how lighting and temperature can affect customer sales. Firstly, the optimal temperature can cause customers to stay longer in our retail stores, which can increase the chances of our customers buying clothes, thus increasing sales. Secondly, the optimal lighting can benefit the shopping experience of our customers. The proper lighting can make the retail store look more appealing to enter and can also make the clothing items look more attractive, thus boosting sales. Now for the block diagram. For the counter M5stack, we have 5 sensors and units, plus the 3 buttons for input. The angle unit is connected to port B, the ENV and RFID sensor is connected through the PA hub, and the RGB unit and light sensor is connected through the PB hub. Now this gives an output through the LCD display on the M5stack, and it also sends the data of the RFID sensor through ESP-NOW to the M5stack on the shelf. For the block diagram for the shelf M5stack, we have 3 primary inputs: the PIR sensor, which is connected through port B, the TOF sensor, which is connected through port A, and the 3 buttons on the M5stack itself, which will finally display that data on the LCD on the M5stack as the output. Now for the flowchart. We will start with the countercode M5stack flowchart. From left to right, we will start by connecting with the other M5stack at the shelf. We will then display the data coming from the 3 sensors and send the RFID sensors data to the M5stack at the shelf. From then on, we will use logic to check input on the angle unit, the light sensor, and the 3 buttons. On the right, you can see us checking the input on the angle unit, which in turn will adjust the brightness on the RGB unit. On the left, you can see us checking input on the light sensor, which when the light intensity changes, will change the data on the comfortability status. Finally, on the right, you can see us checking for button input, which will be used to increase or decrease the range of values for the light and temperature in the room, which is considered optimal. Now for the flowchart of the M5stack shelf code. First, we will start by connecting with the other M5stack at the counter. We will then gather the data of the RFID sensor and display such data. We will then display the data of the TOF and PIR sensors. From then on, we will use logic to check on the status of the PIR and TOF sensors and also the 3 buttons. On the left, you can see us checking for the input of the PIR sensor, and on the right, you can see us checking input on the buttons, in which if button A or B is pressed, will increase or decrease the TOF close distance. Finally, we will check on the TOF sensor to see if someone is nearby the shelf, and to also check how long that person stays nearby that shelf. Now, I'll be passing my time on to Jiawei, who will be talking more on the demonstration of our prototype.
Here's our live demonstration of how everything works and the overview of our whole prototype. Here's where we use angle unit, light sensor, and RGB unit. As we turn the angle unit, the RGB unit gets brighter or dimmer. The light sensor will then record the brightness of the room and send the data to the M5stack. The brightness value and comfortability will change as the brightness of the room changes, and the brightness of the room will be kept at comfortability perfect. We use the 3 buttons of the M5stack to change the light maximum, minimum, and temperature maximum and minimum. By pressing the A and B button once, it increases or decreases the light min or light max, while by pressing twice, it increases or decreases the temperature max or min. The last button is used to hover between temperature max, temperature min, or light max or light min. During the payment, as customers scans their items at the counter, the RFID catches it and records it down. The data will then be sent to another M5stack, which will be showing all the data being collected. At the shelf, when an item is being lifted, the PIR sensor catches the motion and records the number of times where the shirt is being picked up. Lastly, the TOF sensor will sense the amount of time a customer spends on an item. The timer only starts going only when a customer stands for 10 seconds in front of an item. The 10-second waiting time will provide us with accurate data to prevent some people just walking past the shelf.
This concludes our presentation. Hope you liked it. Peace out.